Well, thank you very much for inviting me to give this talk today. Must admit, I have actually got an introductory slide about me in my talk, but I'll run through that very quickly, get in a few moments. So my background, I did a master's in chemistry at York, and I graduated in 2012. Then followed that with a PhD in chemistry, also at York, working in the research group of David K. Smith, and my topic was on hybrid and multi-component hydrogels, and I completed that in 2016. Joined King's College London pretty promptly after my viva in 2016, again as a teaching fellow, and since then I've excuse me, become a lecturer in chemistry education in 2019, and following that a senior lecturer in chemistry education as of this year. So my role in the departments at King's is to predominantly deliver teaching for the departments. So I deliver lectures in organic and supramolecular chemistry, and I'm in our teaching labs across our sort of first 3 years supervising our undergraduates. I work in a lot of educational research, so areas such as active learning, inclusive education, and practical development. I'm also the undergraduate admissions tutor for our department here, and I'm also involved in outreach as well. And it was doing some outreach, I think about 6 years ago now, when I gave the first version of this lecture, and it was recorded and put online. And that's how I think Peter found me and invited me to give this talk today. I was asked to dress up again, so I will just stand up because you can't quite see, but I have got the full frock coat and waistcoat on today if I don't disappear there. My talk today is a bit sort of history of chemistry and a bit of history as well. I'm very interested in general in the history of chemistry, particularly poisons, as might become obvious as we go through this talk, but also history in general. So there will be quite a few bits about general history associated with the time that I'm talking about. I also really like ghost stories, very appropriate for A Christmas Carol. I'm also into cooking and foraging as well, and those will both become relevant as we go through the presentation today. I'm just going to finish my introduction with a short apology. I've had a bit of a cold the last few days, so I'm very sorry if I wind up having a coughing fit to rival Tiny Tim as we go through the talk today. So do please bear with me if I have to just stop and take a pause on that.
Okay, well, thanks, Anne, and I hope you don't have too many problems. Do you have a glass of water standing? Do you have a glass of water with you? Okay, very good.
I have, yes.
Dan, hopefully you can now begin your talk. So please tell us about the Christmas Carol or the chemical.
Brilliant. Okay, so if you bear with me just a moment, and I will get my screen sharing for you. Okay, so just to check, can everybody see the screen there? Is that okay? And is that coming through all right?
Yes, I can see it. It's fine.
Excellent. Okay, so as I said, thank you very much for inviting me to give this talk today. So this talk is entitled A Chemistry Christmas Carol, being a scientific investigation of a literature classic. And there we go. So I've already given you the introduction to myself, but just to remind you, all those details are there on the screen. And that means I can get straight into the talk itself now. So I would like you to come back on a journey with me through time exactly 180 years ago to London in 1843. So just to set things in context about what's happening at this time, we're of course during the reign of Queen Victoria. At this point in history, her husband Prince Albert is still alive, and in 1843 they have had the birth of Princess Alice. I think this photo was obviously, well, not photo, this portrait was a few years after her birth. Prime Minister at the time is Robert Peel, who you may know for his association with the modern police force. It's been a bit of a quiet year in London for chemistry. In the research that I've done, no really notable developments that I could find, although audience members may wish to correct me on that. But further afield, we have had things like the naming of lactose by Jean-Baptiste Dumas, the discovery of the elements terbium and erbium by Carl Mosander, and the production of single-acting baking powder by Alfred Bird, the same Bird of Bird's custard, which of course may be making an appearance on many Christmas dinner tables. This year in London has probably been a better year for things like engineering and technology. Probably the biggest development was the opening of Brunel's Thames Tunnel. That was both the Brunels, Mark and Isambard, responsible for constructing this tunnel, and it's still going 180 years later, although now, of course, it is part of the East London line. If you're wondering how I got that photo, because it looks like I'm standing above the tracks, I was standing above the tracks because it was open to go down on foot a few weeks ago, and it was still very Victorian architecture down there, which was a great experience to do. Also in 1843, Charles Babbage, who you may have heard of for his early sort of computing work, his analytical engine, or at least part of his early analytical engine, was displayed at the King George III Museum here at King's College, London. And associated with that, we have Ada Lovelace in 1843, developing an algorithm that would enable the analytical engine to calculate a sequence of Bernoulli numbers. I'm not a mathematician, so I'm afraid I can't give you any more information than that they are Bernoulli numbers. This was regarded as the world's first computer program. And just to round things off, for those of you who like sort of civic engineering, 1843 was the year that Nelson's Column, which is not very far from King's College, London, was completed. And at almost the other end of the Strand from Nelson's Column, in the publishing house of Chapman and Hall at 186 Strand, on the 19th of December, 1843, so as I said, exactly 180 years ago, we have the publication of Charles Dickens' A Christmas Carol, which is a ghost story of Christmas. This book would sell out within 5 days. It was sold out by Christmas Eve, and it would have 12 reprints by the end of the following year, 1844. Just to give you an idea of what Dickens was like at this time, this was quite early on in Dickens' writing career. He looks quite young at this point. This is a portrait of him from 1843 by Margaret Gillies. He's not the kind of the bearded old man that we probably associate with the image of Dickens now. At this point, he is still quite young. As I said, it's early in his career, and Christmas Carol, I think, was really, for him, it was a pivotal book. He was quite short of money at the time, and he really needed to get something published and have it be a success, which it was. Dickens at this time was very much seizing on a movement in society where Christmas as a holiday was undergoing a real revival or reappraisal. Christmas had never been the most significant holiday in the Christian calendar. That's Easter. That's the death and resurrection of Jesus. That was the most significant holiday. It had really been in decline as a holiday since the Middle Ages. You know, we'd had the rise of Puritanism in England, and by sort of the Georgian era, it was kind of not very well celebrated. Maybe people took a few days to celebrate it, but business more or less carried on as normal. It wasn't even an official holiday. But in the early 19th century, Christmas is starting to make a comeback. We have Christmas trees have been introduced in the 18th century to the UK, but they were popularized by Victorian Albert. Christmas carols were undergoing a kind of a reappraisal as well. They were making a comeback. And Charles Dickens really seized on this, and this is why I think Christmas Carol has done so well to survive and become so popular as it is today. It wasn't his first Christmas story, but it definitely was his most successful. It's probably one of his most famous stories overall, probably up there with things like Great Expectations and Oliver Twist. Probably the three stories most people would say when you think about Charles Dickens stories. It's A Christmas Carol, Great Expectations, Oliver Twist are the three that certainly come to mind for me first. It's possibly also the most famous Christmas story outside of the Christmas story, the Nativity, certainly in the Western world. It has been adapted countless times for stage, for TV, for radio, for film. There's no definitive list of how many adaptations there have been made, nor how many works it's inspired, how many times it's been referenced, satired, how many homages there have been to it. If you've never seen an adaptation of it, which I feel like is probably unlikely, but certainly for people of my generation, I think we generally consider our definitive adaptation of it to be the Muppet version of it. Disagree with me if you will, but I think it's probably, despite its use of puppetry, it's definitely very close to the original story. And Michael Caine is a fantastic Ebenezer Scrooge in that adaptation. So if you haven't read the book of A Christmas Carol, it might surprise you to find out the structure of it. Dickens actually divided it into 5 staves based on the lines you have on sheet music. And each of the staves formed the kind of the 5 main parts of the story. So in stave 1, Scrooge, we meet Scrooge. He's a very miserly character. It's Christmas Eve. He's being mean to his clerk, Bob Cratchit. He's refusing to donate money to charity. He's leaving urchins out in the cold. And he goes back to his very large house, which he doesn't heat very well because he doesn't want to spend the money on fuel. He has his dinner. He settles down in front of the fire. And then the ghost of Jacob Marley, his old dead business partner, appears And Marley is in chains, very heavy chains, and Marley says to Scrooge, "You're going to have chains like this yourself in death if you don't repent and change your ways. And you're going to be visited by 3 more spirits who are going to try and make you a better person." And so these are the 3 spirits that we generally associate with the story. So stave 2 deals with the spirit or the ghost of Christmas past. Stave 3 deals with the ghost of Christmas present, and stave 4 deals with the ghost of Christmas yet to come. And then after being visited by these 3 spirits, Scrooge becomes a changed person. And in the final chapter, he kind of repents and redeems himself. And notably, he brings Christmas presents and Christmas gifts to his clerk, Bob Cratchit, and Bob Cratchit's family, including his wife and his son, Tiny Tim. So that's the overarching story of A Christmas Carol. What I'm going to do in this talk today is I've used each of these 5 chapters to conduct an investigation of an area of chemistry. Some of it's chemistry past, so very much Victorian era chemistry, and some of it is more based around maybe some more myths associated with kind of chemistry and the supernatural and Christmas time. So I hope you find these interesting. So I've entitled my first stave "Bah Humbug." It's probably the expression, well, one of the expressions most associated with A Christmas Carol. It's the expression of kind of disgust or dismay that Scrooge emits when he's asked about Christmas. Bah humbug. He doesn't want to celebrate it. It's passed into our kind of lexicon now, our vocabulary, as something we say when we don't want to get involved in Christmas celebrations. But of course, humbug is also the name of a sweet. And you might notice I've titled this slide "A Scrooge of a Sweet Maker." So this story takes place back in the 1850s, and this is associated with a sweet maker called Joseph Neal, who made these peppermint lozenges, as they were called, or humbugs as we know them today, in Bradford. So this was taking place in 1858, and at this time the cost of sugar was 6.5 pence, so that the D is the old pence, per pound. That was quite expensive for the time, and one way that people got around having to pay a lot of money for expensive ingredients like sugar was to adulterate their ingredients in the sweets that they were making. So someone had worked out that you could replace some of the sugar in sweets with a substance that was often called daff or daft, and this was plaster of Paris, which is also known as gypsum, which is also known as calcium sulfate. And the cost of calcium sulfate was significantly less than that of sugar. It was 0.5 pence per pound in October of 1858. And Neal, as a sweet maker, would make his sweets in great big batches. He worked out that he could replace 12 pounds of sugar in his recipe with 12 pounds of gypsum. And I did a bit of a currency conversion of this, and that gave him a total saving of 72 pence, which works out as 6 shillings at the time. That's about 18 pounds in modern currency. Obviously, it doesn't seem like a lot, but obviously, you're a business, you want to economize where you can. So that was 12 pounds of sugar out of what should have been, to my recollection, about 52 pounds of sugar. So he was replacing roughly 1/5 of the sugar content with gypsum or calcium sulfate in there. I first encountered this story many years ago, and ever since then, I've been looking for an excuse to try and actually make these sweets, because a lot of the sources give all of the quantities that are used. In particular, you'll note my reference there, John Emsley, The Elements of Murder, gives the amounts used in this, and you might be able to tell based on that where this story might be going. So I'm hoping this video is going to work. So I had a go at making these at home, and I obviously reduced the quantities greatly. I didn't want to be making about 40 pounds of sweets, so I did some conversions and had to do a little bit of improvisation around the recipe. So the list of ingredients survives, but the original recipe doesn't. So I've used a bit of some recipes online and a bit of my own know-how from both chemistry and cooking to make these sweets. So if you want to make these at home, not that you should, but if you want to try and make these at home, what you'll need is 160 grams of caster sugar, 12 grams of gum arabic, 1 milliliter of peppermint extract, and 48 grams of daff. And I'll just pause it here. So this was gypsum. And I did check that this was suitable for consumption. So this was actually sold by a brewing supplier. So you can still buy gypsum for brewing purposes. It's used to Burtonize the water. It makes it similar to the water in Burton-on-Trent, but you might be able to read the label there. It lowers the pH of the mash in beer brewing and increases the hardness of the water. So bought this online. It was perfectly safe for consumption. So don't worry, I wasn't going around getting lab grade the calcium sulfate. And then I put all of the dry ingredients in the pan and added 60 milliliters of water to this. So that's everything except the peppermint extract in there. This then went onto the stove, and you can see I've got a thermometer in there to measure the temperature. So I'm trying to stir this to get the sugar and gum and daff to dissolve in there. Took a little while, but it did eventually go. And then I'm getting the pan heated up. It gets quite hot and quite vicious. And I'm trying to heat it up to the hard crack temperature, which is about 154. So it started to go a bit caramelized at this point. Here I'm adding in the peppermint extract. And then I took the pan off the heat and poured the mixture into a greased tin. At this point, you're supposed to try and mold it while it's still very hot. And you have to have greased hands to do this. This was very unpleasant. I was trying to pick it up out of the pan and pull it to make it into like a rope and knot it together. It took me a little while. I didn't film a lot of it because it was very hot and I had a lot of grease on my fingers at this point. But eventually I was able to get this mixture to harden, cut it, make it into a rope and cut it into small bits of sweets, and then left these on a buttered tray. And then I filmed my initial reaction to trying these. So hopefully you can just about see what they look like there. Right, well, here we go. Okay, first impressions, I'm they're a bit chalky. They're sweet, there's a mild peppermint flavour there, but yeah, I'm not sure I would recommend making them. Okay, so if you couldn't quite hear what I said in that video, sorry, because also as I was filming that, my cat was outside the kitchen door meowing to be let in because he wanted to lick all the greasy trays. Basically, I tasted them. They were very chalky. I think that was from the calcium sulfate in there. They're sweet. I couldn't taste a lot of peppermint. I'm not sure if the peppermint extract I was using was weaker than that in the Victorian era, but I can't say I can recommend making them. I have probably had about 2 dozen or so of those there. I've only eaten one of them. I think my wife's eaten one as well, and the rest went into a jar, and they're now probably somewhere in the back of a cupboard. So yes, those are Victorian humbugs, but what does this have to do with the elements of murder? So these humbugs, in October 1858, about 30th of October, sweetmaker Neil, he sent his lodger, James Archer, to purchase some gaff from a pharmacist called Charles Hodgson. Hodgson at this time was ill in bed, and so he sent his assistant, William Goddard, up to the storeroom. And Goddard had instructions as to where to find the gypsum. The problem was the instructions that Hodgson gave to Goddard weren't very clear. Goddard went up to the storeroom, and all he'd been told is that the barrel was in the corner. So he goes to the corner of the attic storeroom, and there's a barrel there, and he opens it. It's a white powder. He takes the powder out and gives it to Archer to take back to Neil. The problem is, as I said, this barrel wasn't very clearly labelled. In fact, the barrels were only labelled on the bottom, not anywhere on the side. If Archer had bothered, if Goddard had bothered to look at the barrels, he would have seen that obviously one of them up there in a corner contained gypsum, but the one that he'd chosen to take the white powder out of contained arsenic trioxide. So from this point onwards, it was only a matter of time before something deadly happened. The arsenic trioxide was taken back to Neil to make the sweets, but he delegated this to his colleague, James Appleton. Appleton noticed that the finished product looked different from usual, and he later becomes ill, and he has vomiting and pain in his hands and his arms. However, despite the sweets looking unusual and despite Appleton feeling ill, they decide they're going to sell these sweets anyway. They sell £40, which is about 18 kilos, of these humbugs to William Hardacre, who's known as Humbug Billy, at a discount because the sweets look a bit off. Hardacre then proceeds to sell the sweets for 1.5 pence for every 2 ounces, that's about 57 grams, from Green Market in central Bradford. A significant amount, I'm afraid I don't know the exact amount because sources slightly differ on how much was sold, but I reckon it was close to all of them. A significant amount of these poisoned humbugs were sold by the close of business that Saturday night. In the early hours of Sunday, the 31st of October, Halloween, perhaps an appropriate day for the terror that was about to hit Bradford. The police learned that a 9-year-old called Elijah Wright and a 14-year-old called Joseph Scott have suddenly died under suspicious circumstances. Their symptoms of vomiting and convulsions initially make the police think that this is cholera, which was very prevalent at the time. However, a doctor called John Henry Bell swiftly links the sweets to the deaths as more people start dying, and it's noted that they've all purchased these sweets. The chief constable of Bradford, he orders his officers to get out into the streets to ring bells to raise the alarm about any sweets purchased from Hardacre's stall the previous day. The police managed to recover 36 pounds of these humbugs, so not the full 40 that were produced. The analytical chemist Felix Marsh Rimington tests the sweets and he confirms that arsenic is present in them. Now, the sweets have varying amount of arsenic in them. Presumably the mixture wasn't homogeneous when the sweets were made, but some of the sweets are containing up to 16 grains, as the measurement was at the time. That's 1.03 grams of arsenic in a single sweet. That is enough to kill 4 average-sized people. So what's happening when arsenic gets into the body? Well, in the body, you've got your pyruvate dehydrogenase complex. And this is responsible for converting usually pyruvate into acetyl coenzyme A. Essentially, the pyruvate is split and added onto the sulfur that's on the left-hand side of this molecule. However, if arsenic gets into the body, it starts interacting with pyruvate dehydrogenase complex. What it does is it reacts with parts of the complex, the component simply known as E3, and we have sulfur groups in this. And arsenic in the form of arsenite reacts with some of the sulfur groups that are part of the process of converting pyruvate to acetyl coenzyme A, and it inhibits the reaction. It stops this reaction from happening. That then has a knock-on effect in that it prevents the citric acid cycle from being able to carry out. The citric acid cycle is there to allow cells to respire. If that process is inhibited, the energy system of the cell is disrupted, and that results in cell death. And so that is why arsenic is a very effective and very deadly poison. This poisoning had quite a big fallout. There were at least 20 official deaths associated with this, although the number may be higher, and likewise over 200 were thought to be ill. Again, the number may be higher. Some of these sweets managed to travel to places like Leeds and Bolton, and there wasn't an official tally taken there of how many people had died. This incident was one of the major poisoning incidents that led to the UK Pharmacy Act of 1868, and this not only limited the sale of poisons and dangerous drugs to qualified pharmacists and druggists, but it also established the regulatory framework for the sale of poisons that still to this day requires all drugs to be appropriately labelled. It also contributed to the Sale of Food and Drug Act 1875, which regulated the adulteration of foodstuff, although didn't quite stop it. It still allowed it to happen, but it was much more controlled than it had previously been. If you're interested in what happened to the people involved in this, Humbug Billy, he was never arrested, but he'd consumed enough poisoned sweets that he was left paralysed from eating them. Neil, Goddard and Hodgson, they were all arrested for manslaughter. An inquest only found Hodgson, the pharmacist, guilty, though they did concede that the arsenic had been sold accidentally, and it was mixed into the sweets under the assumption that it was the harmless calcium sulfate. After this inquest, they sentenced the York Assizes for further trial, but the jury there didn't reach the same judgment, and everybody was acquitted in December of 1858. The judge himself was the one who stopped the prosecution against Hodgson. At the time, they said basically no other result was going to be expected. The only criminal thing about the whole incident was that the law could not touch at the time the practice of adulteration and the supply of things like daft for this purpose. And they said at the time, if this calamity teach this lesson, it will not have been useless. And so that is what ended up contributing to these two acts that we have mentioned here. This case has an interesting link to A Christmas Carol, other than just being about humbugs. And that's this illustration that I'm showing you on the screen here. This is called The Great Lozenge Maker, and it was a kind of cartoon made up after the incident. It's drawn by John Leech. John Leech was the illustrator for the first edition of A Christmas Carol. Those are the images you can see behind me here. You can perhaps most notably see his style in this artwork, which is from Stave 2, The Ghost of Christmas Past. And that makes a quite apt lead on into our Stave 2, which is Ghosts of Suppers Past. Now, of course, I've just shown you a bit about the Ghost of Christmas Future coming at the end of my Stave 1 there. And actually my Stave 2 starts with a reference back to Stave 1 of A Christmas Carol. So when Scrooge is first confronted with the spirit of Marley, he doesn't want to believe that he's real. He thinks he's having a bad dream or a nightmare. And Marley's ghost says to him, well, why do you doubt your senses? And Scrooge says, well, because a little thing affects them. You may be an undigested bit of beef, a blob of mustard, a crumb of cheese, a fragment of underdone potato. There's more of gravy than of grave about you, whatever you are, which I think a lot of people think is probably one of the better jokes within A Christmas Carol. It's quite a good pun. I'm picking up very much on the crumb of cheese bit in there because a lot of people still associate cheese as a foodstuff that gives you nightmares if you have it just before you go to bed. And this is a myth that has persisted. And in fact, last week I was talking to someone and they were still insisting that cheese caused nightmares if you had it before bed. In actual fact, there was a study conducted on this. And continuing on the theme of perhaps bad puns, this study was conducted in 2005 by a group known as the British Cheese Board. Just let that sink in for a moment there. But anyway, in this study, they gave 200 participants 20 grams of cheese 30 minutes before they went to bed, and they asked them to record their dreams and quality of sleep for a week. 72% of participants said they slept very well every night, and 67% remembered their dreams, and no one apparently recorded experiencing nightmares. So some of the cheeses that they tried were Stilton. Apparently Stilton gives you the kind of the weirdest dreams out of a lot. They describe these as crazy dreams. Examples included talking soft toys, a vegetarian crocodile upset because it could not eat children, and soldiers fighting each other with kittens instead of guns. Cheddar apparently gives you dreams about celebrities, although I must admit, I looked down the list of people mentioned. I didn't recognize many of them. I think most of them were from Coronation Street and Emmerdale, which I don't watch, although apparently one dream did involve Johnny Depp. Red Leicester apparently gives nostalgic dreams. If you wanted to dream about your school days, long lost childhood friends, previous family homes, this was the cheese to have before going to bed. Lancashire cheese apparently gave people dreams about work, although apparently mostly it was people dreaming about themselves working better careers or more prosperous careers than they currently had. British Brie, the study was very insistent that this was British Brie, none of the French Brie here, thank you very much. Tended to vary depending on whether the participant was male or female. Women tended to experience very nice dreams, according to the study, whereas men apparently had very obscure dreams, such as having drunken conversations with a dog. And then apparently if you wanted a good night's sleep without dreams, then you would choose Cheshire cheese. So this study said as well that they claimed that cheese actually helped people fall asleep. And they did talk a little bit about the chemistry in this, and their suggestion was because cheese has a relatively high tryptophan content in it. So this tryptophan is an amino acid involved in the production of melatonin, which also goes on to produce serotonin, and that plays an important role in our sleep-wake cycle. But a lot of foods are very high in tryptophan, and none of them have this association with dreams or causing good sleep to the extent that cheese does. And in fact, this study didn't have a control group or test any other foodstuffs. There's also a speculative theory that certain cheeses, particularly those like blue cheeses that have a lot of bacterial and fungal content in them, they might contain, or they might have a high amount of compounds such as tyramine in them. And this suggests that tyramine has this kind of psychoactive effect on areas of the brain that are important to our sleep-wake cycle. And that then may alter our dream patterns and unconsciously excite us and give us these vivid dreams or these nightmares that are associated with cheese. I'm going to say ultimately, having looked into this, having looked into more reputable journals and not just trusting the now defunct British Cheese Board in their research, there's very little evidence that supports either of these theories. As I've said, there are other foods that have high amounts of tryptophan and tyramine in them. They are not associated with bad dreams or increased dream activity. It's most likely that the disruption in sleep that then leads to perhaps bad dreams or nightmares actually just comes from eating too close to bedtime. And then it's a person's digestive system acting through the night that is disturbing their sleep cycle. So when Scrooge reels off that list of foods, he was actually right. It's not just the cheese, it could be all the other things, upsetting his system and giving him bad dreams. Okay, so that was stave 2. On to stave 3. So remember, stave 3 is about the ghost of Christmas presents. I'm going to talk to you about some ghosts of the Victorian present here. And can we have a chemical explanation for ghosts? So when I first gave this lecture 6 years ago, I showed this picture on the screen, and my audience was mostly teenagers, and I asked them if they recognized what this structure was, and I think a lot of them didn't recognize it. These were still around quite a bit when I was growing up in the 90s, but these days they are starting to get demolished and used for other purposes. I'm sure a lot of people in this audience recognize them, though. This is a gasometer, and this is used to store gas that would then be piped into people's homes for heating and cooking. And the way this works is it is a collapsible structure or telescopic structure that sits above water, and gas is pumped in during the day usually, and then at night or when in the evening when people want the gas for heating or cooking, the gas will be pumped out and the structure would gradually collapse back down again. Now, the gas that was contained within these structures is not the same sort of gas as we use nowadays for cooking. Nowadays we use natural gas, which is composed of things like methane and ethane, usually found in the North Sea. The gas that went into these gasometers came from the gasworks. This is a picture of a very old gasworks here. And gasworks consisted of a series of ovens, and into these ovens, people would be putting a carbon source. And this would be used to produce effectively a man-made or a synthetic gas. The carbon source here is either coal or coke, and I'm not talking about Coca-Cola or cocaine here. I'm talking about a substance that is produced from coal, where it's heated in the absence of air, and it derives off a lot of organic substances, a lot of volatile and liquid products, and that leaves a kind of a light, very carbon-rich residue. So kind of similar, I suppose, to making charcoal, from which you derive off a lot of the volatile organic products, and you're left with a lot of carbon. And in these ovens, you would put your carbon source in, and if you blow air across them while you're doing this, you get carbon monoxide as a product. But it was also worked out that if you, as well as just having air, you had steam present in the mixture as well, then the steam or the water in the steam would react with the carbon, and that would produce not just carbon monoxide, but also hydrogen as well. And the mixture of carbon monoxide and hydrogen gave rise to this town gas or syngas or coal gas, as it's varyingly called. And this was a very, very flammable mixture. There were a couple of other reactions that could happen in this mixture as well. So the carbon could react with more equivalents of water, or carbon monoxide could react with water, and that would give you carbon dioxide as well as hydrogen there. But usually this gas contained a very large amount of both carbon monoxide and hydrogen. It was very flammable and a very effective fuel for both heating and lighting in the 19th and 20th centuries. Of course, very good reason we don't tend to use this anymore, and that's because we know how bad carbon monoxide is. It's sometimes called the silent killer because you can't smell it, you can't see it, you can't hear it. We know that it interacts with hemoglobin in the blood. So instead of oxygen binding to hemoglobin, if you have carbon monoxide binding to hemoglobin, that happens irreversibly, and you form this carboxy hemoglobin complex, and that prevents and reduces oxygen transport around the bloodstream. This table here just shows some of the varying effects of what carbon monoxide can do at varying concentrations. At low concentrations, some of the acute effects are things like headaches within a few hours. You might feel dizzy, you might feel nauseous. But once we start approaching kind of 0.1%, that can, in the span of about 30 minutes, convert 50%, so half of the hemoglobin in your blood into carboxy hemoglobin. That's carbon monoxide irreversibly bonded to your hemoglobin. Once we get to that point, we are seeing headaches, dizziness, nausea very quickly within 20 minutes, half an hour. You might be dead within 2 hours. Once you get to very high concentrations, you're going to fall unconscious very rapidly, and you're going to die very rapidly as well. That is what happens if you get carbon monoxide in a very large dose. However, chronic carbon monoxide poisoning is also possible, and that's where you get exposed to very small amounts of it, but very, very frequently. Say, for instance, if you've got a gas lamp fixture in your house and it's ever so slightly leaky, and you're just breathing in a very small amount every so often. And in fact, it's noted that the chronic symptoms of carbon monoxide poisoning, as well as the headaches that you get, same as with the acute poisoning, this also causes things like muscular pain, depression, chronic fatigue syndrome, and perhaps most interestingly, hallucinations. And there is quite a good theory that the rise of the use of this town gas in houses in the Victorian era was what contributed to a rise in seeing these apparitions, so spectral apparitions. So it might be that carbon monoxide is actually a chemical explanation for why ghosts were becoming more popular and were seen more often during the Victorian era. I suppose just a little interesting aside, about 18 years ago now, there's actually an episode of Doctor Who called The Unquiet Dead that has Charles Dickens in it, Ninth Doctor and Rose as well. And they actually use gas in a house as a way to defeat the gaseous aliens there as well. So I think that's quite a nice link between this and The Christmas Carol. And in fact, that leads quite nicely on to my next story. So talking about Charles Dickens and moving into stage 4 here, where we talk about ghosts of the electrical future. So in that Doctor Who episode, The Unquiet Dead, Dickens is actually in Cardiff. He's performing on stage, doing a reading of A Christmas Carol. He'd started doing these in 1853. He gave over 100 performances of the book on stage right up until 1870, the year of his death. Christmas Carol, of course, has been adapted for stage even before Dickens started doing these readings as well. And if you're going to go on stage and do readings, you want to make sure that you are well illuminated. So theatre lighting during the 19th century, there were kind of a couple of ways, or a few ways, that this would work. One of the early forms of theatre lighting that we had, or very bright theatre lighting that we had, was limelight, and you might recognize that phrase. We still use it today to describe people who are enjoying a moment of celebrity. We say that they are in the limelight. Limelight is just an intense illumination that's created when you have a flame fed by oxygen and hydrogen, and you direct it at a cylinder of quicklime or calcium oxide. This can be heated to very high temperatures, over 2,500 degrees Celsius, before it will melt. As it's heated, it gives this very, very bright white light, and you can direct it using mirrors and lenses at the stage. So that was a very early form of theatre lighting, but later on in the 19th century, it was superseded by another form of bright light, and this was the arc lamp. So this illustration here depicts a carbon arc lamp, and this is where you have an arc of electricity going between two electrodes, and this electricity is essentially ionizing the gas in the air and causing this bright white glowing light. Arc lamp was invented by Humphrey Davy, very prolific chemist in the early 1800s. The exact date he invented it, we don't actually know. Lots of different records for this, but it was very early 1800s. The way that he did it was he put a load of electrical cells onto this and would pulse a very high voltage through two carbon electrodes. The carbon electrodes will be touched together at the start, and then they will be gradually pulled apart as the current was going through them. And that would essentially strike or ignite the arc between them. Then the electric current would heat and maintain this arc light as it goes between them. The rods, the carbon rods, they are slowly burnt away in use because it's very, very hot. They are being vaporized. And so the distance between them has to be maintained and controlled to maintain this very bright white light arc. Davy, in his initial lamp, he was using charcoal sticks as the carbon rods. So that's both the electrodes in there. His battery, I'm showing a picture of one on the screen here. This is an early arc lamp. You'll note that has, I think, 12 early electrochemical cells attached to it. Davy's very early one had a 2,000 cell battery attached to it, but that would create an arc across a gap of 4 inches or about 10 centimeters. So quite a large arc for the time, and would produce a very bright white light. So obviously, if you're going to be producing this amount of light, you need this amount of energy, you are going to need some very, very reliable electrochemical cells. So of course, I can't not talk about the 19th century chemistry, electrochemical cells, without talking about one of the famous figures from King's College, London. So this is John Frederick Daniell. He was the first professor of chemistry at King's in 1831, so actually a few years before Christmas Carol. He was a very prolific chemist, also meteorologist at the time, but he's perhaps best remembered today for inventing the Daniell cell. And this was the kind of first reliable electrochemical cell. He invented this in 1836, and it consists of a copper pot that he filled with copper sulfate solution. And inside of that, he immersed an unglazed earthenware container, kind of like a terracotta pot, that was filled with sulfuric acid and a zinc electrode. What he was trying to do with this invention was to find a way to eliminate some of the issues that were found with the voltaic pile invented by Alessandro Volta, because the main problem of that voltaic pile was that it produced hydrogen gas. And so he was using a second electrolyte, the sulfuric acid here, that was designed to consume the hydrogen produced by the first. The reason he uses earthenware pot was it was a kind of semi-porous barrier. It allowed ions to pass through, but it kept the solutions from mixing. The downside of this cell was that the copper, you had copper buildup in the pores in the earthenware pot over time, and it would reduce the battery's life. However, this did prove to be a much more reliable electrochemical cell than the voltaic pile because it wasn't producing hydrogen. We had copper being deposited on one of the electrodes in there as well, on the cathode, whereas in the other one you get hydrogen deposited. Copper can conduct and keep the current going. Hydrogen was an insulator and would prevent the current from moving. The cell was also safer, and surprisingly, despite the fact it's got sulfuric acid in it, was actually less corrosive than the voltaic pile as well. If we try and build these nowadays, we do still make these sometimes in our teaching labs here at King's with our students, but we tend to do them as half cells rather than the complex porous pot method, although we do somewhere in King's have one of the original ones. Unfortunately, I wasn't able to find it to get a picture for the talk today. We see your half reactions here. You have zinc going to zinc 2 plus and producing 2 electrons that flow through the circuit. And then at the other end, you have copper being reduced by reacting copper 2 plus with 2 electrons to give copper metal. And that's deposited on the electrode. The Daniell cell generates approximately 1 volt. It's closer to 1.1 volts, but it is actually the cell that we get our kind of modern definition of the volt from as well. And it was these type of electrochemical cells that Daniell invented, and then there are a few others based on this as well that were also very reliable cells. And it was cells like these and the batteries that were made out of multiples of these cells that pretty much were responsible for powering the electrical industry in the 19th century up until the electrical generator or the dynamo was invented in the 1870s. And so what I'm kind of trying to say here is that these electrochemical cells were the ones that were going to be used to reliably power some of our theatre lights, like the arc lamp. And this would allow for something in the Victorian era that they were very fond of as a form of entertainment, or may have contributed part of it. And this was a type of theatre show known as phantasmagoria. And this was kind of an illusion, optical illusion, kind of very theatrical stage show where the guests, the audience, would see apparitions throughout the theatre. And the way this was done was you'd have a very bright light bouncing off of some mirrors, passing through some filters that had images in them, and that would be reflected up and shone into a cloud of smoke or steam or something like this. And so this was kind of an early form of almost kind of a holographic image, or a projection, projected image up into these clouds of smoke. So I don't have any direct evidence of Daniell cells powering these arc lamps, but these were the type of performances that needed very bright sources of light. So here we have potentially another chemical explanation for how people were able to see ghosts in the 19th century. It's all thanks to electrochemistry. Okay, so to finish off, stave 5, Christmas greetings. So we've seen past, present, and future. And Scrooge, as he goes through the journey of seeing past, present, and future, obviously he becomes a changed person. And coincidentally, again, in 1843, this was the first year that the first Christmas card was published, or the first commercial Christmas card, and this is a picture of it here. I'd like to think that if Scrooge had been a real person, he might have started sending Christmas cards year after year to his friends and family. Perhaps he would be sending one to the Cratchits and wishing them a Merry Christmas. This first Christmas card, perhaps quite a traditional image, shows a family gathered around drinking what looks like wine or sherry, some Christmas greenery associated with it, and perhaps images of people giving alms to the poor. Victorian Christmas cards got weird very quickly following on from this. They were particularly fond of having ones where frogs were being murdered. They like to see things like mice riding lobsters, rather weird snowmen kind of melting and lurching towards terrified children, monkeys doing portraits of dogs, and frogs dancing with various insects and beetles. The official explanation of this is that these were kind of the memes of the day, and people would send them to one another at Christmas. Oh, have you seen this meme? I think you might like this picture, and also Merry Christmas. One image that also starts creeping in around about this time, kind of late 19th, early 20th century, on some Christmas cards, is the fly agaric mushroom. You might be able to guess why. Maybe this features on there based on its color. And fly agaric has a curious association, an oft-repeated story about how it's associated with a famous Christmas character. So within fly agaric, there's a particular molecule, and this is called muscimol. And this interacts with the GABA receptor, the gamma aminobutyric acid receptor, in cell membranes. And when it's usual, the usual molecule, the GABA, binds with this receptor, what you get is your excited nerves being calm. You have a relaxed feeling. When muscimol binds to it, though, however, you actually start getting an imbalance of neurotransmitters. You start seeing hallucinations, and you think you have apparent superhuman abilities. This was first noticed by people observing reindeer consuming fly agaric fungi, or was apparently first noticed by people seeing reindeer consuming these fungi. Now, somebody somewhere tried to consume these mushrooms and found that they were quite toxic to humans if you consume them just by themselves. However, someone then had the clever idea, and goodness knows how they ever thought of this, was reindeer don't seem to be that affected by it. They seem to go a bit funny. They like prancing around, but they don't die. What if we collect the reindeer's urine and try drinking that instead? And maybe that will give us the high. Again, don't know why they thought this, but whoever thought it was actually right. The reindeer processed a lot of the toxins, but still excreted muscimol in their urine. And so people in the lands where reindeer were present started collecting reindeer urine after they noticed them eating these mushrooms. And they would drink the urine, and they would have lots of visions. A popular reported one was seeing flying reindeer going through the sky. It's reported that this experience, these hallucinogenic trips, were carried out by shamans in areas like Siberia and Lapland. And then at the end of their hallucinogenic experience, they would return to their communities and enter the yurts there. Now, this shows a yurt in summertime, but in winter, that door would be shut. There'd be snow up around this. And the idea is that the shamans would enter the yurt via the hole in the roof. And they would go in and they would meet important people in the community to share their visions. And they would be bringing a gift of knowledge with them. So we have flying reindeer, we have a red and white mushroom, we have people bringing gifts and entering through what is effectively the chimney. And a lot of people say that this is the origin of our famous figure, Father Christmas. Unfortunately, I'm afraid Father Christmas is not a mushroom, he's not muscimol. This is really quite a big myth. Father Christmas, or Santa Claus as he's called, actually comes from a couple of different sources of folklore. He comes from St. Nicholas, who is derived from St. Nicholas of Bari or Myra, and here he is depicted in his red and white bishop's Cornwell-Groves, and he would give gifts to those in need, especially children. Father Christmas, who we now kind of associate as being Santa Claus, was actually originally a completely separate person. He was very folkloric, and he was kind of depicted as kind of wearing more sort of like a big winter coat. He'd have a very long white beard, wear crowns of holly. So these two characters kind of got smushed together, partly through authors, mostly American authors like Washington Irving and Clement Clark Moore, depicting St. Nicholas, and then our British Father Christmas, or English Father Christmas, got mixed in with that myth, and that's why we now have this character today. So he's not invented by Coca-Cola, he's not invented by mushrooms, he's actually invented by, or put together by, a few different sources and a few authors who were coincidentally all writing about the same time as Charles Dickens was. So I hope you've enjoyed this look through some chemistry associated with Christmas, bit of chemistry past, bit of chemistry present, some bit of myths as well. All that remains for me to say at the end of this talk is thank you very much, and to wish you a Merry Christmas. And as Tiny Tim says, God bless us, everyone.
Okay, thank you very much, Tom, for that wonderful talk where you weave Dickens and history and chemistry all together. So very interesting. A lot of biochemistry as well, which is interesting. So thank you very much for that. I have one question myself, and we have one other question. Let me begin with the other question first, and that is, how widespread was adulteration in 19th century England? I mean, I remember, for example, they used to fake tea, which would mean to take spent tea and paint it with Prussian blue and then sell it again. So just how widespread was adulteration in that period, apart from just sweet?
I mean, I'm not sure if anybody has been able to put an exact figure on it, but there was pretty much no regulation on it in the 19th century. From what I found from my research, it's only after we have incidents like this Bradford sweet poisoning and a few other incidents that they actually start regulating it. So, to my knowledge, it was incredibly widespread, and it was very easy to get away with it at the time until this legislation came into force.
Well, of course, the legislation, the Pharmacy Act itself of 1868, had lots of loopholes in it. For example, a pharmacy could open a business and then it would be run by non-pharmacists. In fact, somebody I've just been writing about, a plug for my book here, I've just been writing about Henry Roscoe, and he tried to bring in an act in the 1880s to strengthen the Pharmacy Act. He didn't succeed, but eventually a strengthening act was brought in the 1890s.
Mm-hmm.
In fact, he actually mentioned in his autobiography, he actually mentioned the Bradford story, but I didn't pick up on the fact it was the Bradford incident. So my book is not as good as it should be as far as that. I think. Anyway, I've got a question myself, which also, in fact, actually stems from my biography of Roscoe. And that is, you're talking about the Daniel cell, and I can understand that somebody working at King College, you're very keen on the Daniel cell. But I'm wondering if by the 1850s, 1860s, would it have not been more likely that they would have used Bunsen cell?
Yes, I think so. Obviously, the Daniel cell was the first one, but I think as we progress through the 19th century, other cells do supersede that. They become more reliable. I think they work out they can get higher voltages through different combinations of metals and solutions. I'm afraid I'm as you might have guessed from my background, I'm not an electrochemist by training, and obviously my talk about the Daniel cell is because it's chemistry associated with us here at King's College. So I always like to try and talk about our kind of first chemistry professor when we talk about history of chemistry. But yes, certainly his was not the only cell, and definitely others would have probably produced a more reliable or higher voltage than that within a few years.
Yeah, but the trouble with the Bunsen cell, and I've just been Googling this on Wikipedia while you were talking, the one problem with the Bunsen cell is that it produced nitrogen dioxide as a byproduct, so not very ideal, though it did have a very high voltage. It volted with about 2 volts, and I believe it was very stable. Who mentioned the Bunsen cell a lot is Jules Verne in his story. The Nemo submarine, for example, is run on Bunsen cells, which must have been dreadful. Water with all that nitrogen dioxide being produced, but he obviously wasn't thinking through all the practical implications. So anyway, so that's our 2 questions. We have a few comments about apparently you should talk about gas hoses, not gasometers. They're very
I should. I saw that comment. I thought, oh yes, you have made that. You are correct. They should be called gas holders. Sorry, I was always brought up being told they were called gasometers, and that's still a bit stuck in my my head, unfortunately.
not to worry, not to worry. I'm just mentioning it could have been mentioned. It's also been mentioned, but in other countries like India and China and so forth, adulteration is unfortunately all still too common, which is sad and depressing. Okay, well, thank you very much, Dan. I won't detain you any longer. Thank you very much for giving a wonderful talk. We had a total of 53 people, which, bearing in mind it wasn't our usual time of 2 o'clock because unfortunately we had a prior engagement at that time. And because it was near Christmas, I think 53 is an excellent audience and a great credit to you that so many people were attracted to this talk. So meanwhile, everybody, I hope you have a Merry Christmas and a Happy New Year. And in January, our very own Alan Dronfield will be talking about who really invented the Haber Bosch process. So join us again on the third Tuesday of January at our normal time of 2 o'clock to hear Alan talk about the Haber Bosch process. So in the meantime, have a good Christmas, and I look forward to seeing you on the new year. Thanks again, Dan, and hope you have a good Christmas.
You're welcome. You too. Thank you very much. Merry Christmas.
Bye. Thank you, Dan. Bye.